Thank everyone for the afternoon slot. Pleased to see that a fair number of you are still here. Okay, so it's a real pleasure to introduce our first speaker this afternoon is Barbaros, and I'm not going to pronounce our university, but he's affiliated with Queen Mary University and works affiliated with Royal London Hospital, and he's going to tell us about a framework to present Bayesian network to domain experts and potential users. Thank you, Barbaros.
Thank you. Hello. So I'll present an attempt to present Bayesian networks to experts and users who do not have any technical knowledge about Bayesian networks. And I mean, in today's session and in yesterday's session, it has been discussed several times that one of the main challenges of using Bayesian network in legal domains is to describe the model to the jury or to judge or to lawyers. So the framework we developed was actually built for a medical problem. So we built this framework to describe the model for a doctor who also does not have any technical knowledge about Bayesian networks. But in my presentation, I'll argue that most of the challenges in medical models and legal models are similar for Bayesian networks. And I'll also argue that this framework with a few minor modifications could also be useful in legal domain. So I'll first start with similarities of challenges between clinical and legal models. So in both clinical and legal domains, the outcomes of decisions are critical. It's more or less a matter of life or death in both cases. And because of these critical outcomes, in both domains, users want to understand a Bayesian network model before using it. Okay? Or in other words, they won't use the model if they don't really understand it. And this is a shared challenge in clinical and legal domains. Another challenge that exists in both of these domains is that, you have different worldviews between different sides in legal domain, and in clinical domain you have different understanding of the same disease between different doctors. So when we build a Bayesian network model, we usually stick with one view, but we still need to acknowledge the other worldview, and we need to make our assumptions explicit. Let me give an example about it. Here you see a medical model about the traditional understanding of how cholesterol works and is related with heart disease. And this model says if you have a high-fat diet, that raises your cholesterol levels, and your cholesterol levels increases your risk of having a heart disease. And if you take statins, then that decrease your cholesterol levels, and it will decrease your risk of heart disease as well. So this model is shared by many experts. Most drug companies also follow this worldview in terms of cholesterol. But we also have another model which is maybe equally valid, which many clinicians believe it's valid, saying that, it's not the cholesterol causing heart disease, it's the thickening of artery wall causing heart disease. And cholesterol is just a sign of that, because when your artery wall thickens, it happens to contain cholesterol. And if you take statins, that will decrease your cholesterol levels, but not necessarily the risk of having heart disease. So these two models don't fit with each other. They are different worldviews for the same clinical problem. And we don't know which one is true. Some experts claim that the one on the left is true, and some experts claim that one on the right is true. In a practical sense, when we build a decision support model for a physician, we stick with one of these models, or maybe if there's a third model, but we stick with them. But still, we need to acknowledge that the knowledge about the other model also exists, and we made assumptions to stick with the one on the left. So in other way, we need to make all our modeling decisions and assumptions explicit in the Bayesian network. In legal cases, so the differences of models between the defense and prosecution often happens. They usually have different stories, and it may not be possible to build the same Bayesian network structure for that. A very simple toy example. For example, the prosecution might say, well, he was at the murder scene, he committed murder, and that's how this DNA got on the victim. And the defense may have an alternative model saying that, well, we were together that day at a crowded bus, that's probably when my DNA got on him. But then I got off the cinema and I went to the cinema with my wife when the murder happened, so I didn't do it. So again, these are alternative, these are models of alternative worldviews. I won't deal with I won't talk about how to deal with them quantitatively. I think you'll hear interesting talks about them tomorrow. But still, if we stick with one model, we need to acknowledge the other scenario, the assumptions behind this model and other model, and make those explicit in some way. So there are, of course, other similarities between clinical models and legal models, but those two are the main ones we'd like to tackle with this approach. Okay, so Bayesian networks have unique properties to deal with this. For example, they have graphical structure which makes some things more clear than other modeling approach. They have their graphical structure is suitable for our causal understanding of the domain, and the relations and conditional independence assertions are clear in a Bayesian network. But this is not enough to deal with the challenges, deal with the cases I just mentioned. I mean, these are obviously advantages compared to some other models, but these alone are not enough for a Bayesian network model to be understood by any expert. And this has been discussed several times in this workshop and before. So our vision is to have Bayesian network models that can be browsed, reviewed, criticized, and modified by domain experts or users who do not have any technical knowledge about them. So we would like the experts or users, either this is like lawyers or doctors, to browse a Bayesian network, to see the assumptions behind it, to see the knowledge behind it, and to actually be able to criticize it or, recommend modifications. And for this vision, for this aim, we developed a framework to present Bayesian networks. Our framework has two aims. First, we'd like to organize the data about this knowledge and assumptions behind the Bayesian network model. We'd like to show what evidence supports the model and what evidence conflicts the model. And we would like to have a robust structure for that. And secondly, we would like to have a way, an interface to present all this information to a non-technical expert. So these were our aims. And as we developed this model for a clinical case initially, we called it Clinical Evidence Framework. But clinical evidence and legal evidence have sort of different meanings in terms of Bayesian networks. So in legal models, when we talk about legal evidence in a Bayesian network model, we often mean the observations entered to the BM model. But for a clinical model, the observations entered to the BM model are called observations or measurements or tests. And when people talk about clinical evidence, they actually mean the knowledge supporting or conflicting with the BN model, the BN structure we have. So we called it clinical evidence framework because what we want to show is these knowledge and assumptions. What we want to show is to make these knowledge and assumptions clear and explicit, we won't deal with entering evidence and any of that stuff. So, I mean, at this point, I'd like to clarify that when I say clinical evidence from now on, I mean the knowledge, papers, expert knowledge or data supporting the modeling decisions we have made. I'll give a simple example about that. For example, this is a very simple model which says smoking causes cancer. And if I talk about clinical evidence about this model, I'll mean that the reason why that arrow exists and why it's pointed from smoking the cancer. So if I develop something in my clinical evidence framework, it will show all the studies or data or experts who says that, well, smoking causes cancer, okay? It won't have to do anything with, well, either the cancer observed or smoking is observed. Okay, so those were our aims and vision and a brief discussion of the challenges. In the next part of my presentation, I'll talk about the actual structure of this thing. I mean, how this evidence framework looks like. Well, our evidence framework, clinical evidence framework, is composed of two parts. It has a structure and it has a browser. So, our evidence framework has a structure to organize this data and knowledge and assumptions about the modeling decisions. So there is a supporting data structure which has extra information about the Bayesian network model. All the information we can't actually put into a Bayesian network model. I'll talk briefly about how that data structure looks like and what information it contains. We consider a Bayesian network model to have three elements. It has nodes, it has edges, and it has fragments, which you can also you can consider as objects. Okay, so we have group of Bayesian network nodes called fragments. Then we have individual nodes, and we have the edges. And then for each of these, we have evidence and additional information, and I will describe that in more detail. For example, for BN objects, BN fragments, we have a description of what that object means and the elements contained in that object. There is nothing special about BN object, but just more detailed information than what Bayesian network contains. But then for a Bayesian network node, we have in this data structure a detailed description of the node. Because in most Bayesian network models, for example, the model says heart rate, okay? But that doesn't make it clear. Is it the first heart rate measurement, last heart rate measurement, average of heart rate measurement? So we have a more detailed description. We have the description of the states, and we have an explanation of why we chose those states. If it's chosen based on some expert knowledge or some publication, we also make that explicit. We show the numbers in our evidence structure, but we also show where did those numbers come from. So if I define those numbers with a clinical expert, I write the credentials of these clinical experts. So if somebody is not sure, he can contact with that clinical expert. If I get that from some publication, I just put a link of that publication so that you can follow and get more information about it. And I think the most important of all, we have evidence about excluded parents and childs and relations. So all models are simplification of world. All models are wrong. There will be some things, some relations, some variables which are known to have relations with the variables in our model, but we often choose to exclude them for some reason. It can be due to simplicity. It can be that we don't agree with the experts who claims that these relations or variables should exist. So what we do is we still exclude them if it's our modeling decision to exclude these variables or relations, But we make that modeling decision explicit in our evidence framework. So in evidence framework, we say that, okay, we know that there was a correlation between these variables due to this publication or this expert, but we choose not to include this in our model due to these reasons. So in a way, we make our modeling assumptions explicit even when they are related with something not in the model. Then we have the evidence about edges. Again, when I say evidence, it's not observation, it's the knowledge supporting the existing of those edges or conflicting with existence of those edges. So every edge in a Bayesian network models sometimes a causal relation, sometimes a correlation, a dependency. And when we make that modeling decision to include an edge, we better have some rationale for editing it. And in this evidence framework, we also make that explicit, and we also note where that comes from. And yeah, I said we also show where that comes from. And in clinical models, the information, the knowledge behind the model often comes from these three sources. It's either from data, it's the correlations in the data, or it's from a publication, like a previous study says that there is strong correlation or causal relation between two factors, or it is from domain experts. A doctor says that, well, this causes that. So I also show why I included that edge in my model and what was the source for that information. So this was a basic summary of the structure of our evidence framework. So the structure is where we enter all the data and keep them in an organized way so that we can query them, we can change them, or we can even change the structure if we want to. And for this, we use a technology called OWL. I won't go into details, but you can consider OWL as a flexible database to do these things. And the reason we chose OWL but not some other relational database technique is OWL is quite flexible to changes. And we thought, in this domain, there will be a lot of changes in the structure of the database. For example, if this needs to be modified for a legal model, probably we will use a different structure for keeping the data. Okay, so that was where we store all the knowledge and data about all the knowledge and assumptions, but still it requires technical knowledge to browse this data in OWL. It's not practical. So our clinical evidence framework has a second part, which is the browser. So when you enter all this data, all these assumptions about the model, the nodes, relations, and objects, then it creates a website for you automatically. And this website is, of course, much more easy for non-technical people to, non-technical experts or users to browse the model. And we developed this framework for the trauma unit at the Royal London Hospital. So we collaborated with them. We built several decision support models for them. But doctors also don't use models if they don't really understand it. And in trauma, the outcomes are, really critical. So they really demand to understand the model and the evidence behind it. And I'll show how the browser generated from the evidence structure looks like. And I'll actually browse a model with you in the website for one of the models we developed for the trauma unit. And this model, I'll browse, it was developed for a clinical condition called acute traumatic coagulopathy. So acute traumatic coagulopathy is a fatal bleeding disorder. So when trauma patients do bleed, and sometimes under certain conditions, they lose their ability to stop bleeding. And when this happens, if you can't act quickly, they die pretty quickly. So the trauma unit asked us to build a model to predict ATC in first 15 minutes after admission. And yes, and then we built this model. The model is also available to run in this website. You can enter the inputs here, and it will use a generalist to compute the posteriors and show them. But the part of this website relevant to this presentation is the evidence browser. So we recorded all this knowledge and assumptions about this model in the structure I show. And then by using our evidence framework, we generated this website from that model. And in this website, we can find all the information about the variables and edges and fragments. So I would like to first start with the top left one, the fragment called shock, or the box on the upper left side of the model. So when I click that, I can also enter from the left side, but when I click that, it shows me a brief definition of what this fragment means. So this model, part of the model estimates the degree of shock resulting from the blood loss. And then it shows me the variables inside this fragment. Okay, in this description, it's also say that there is a variable called hypoperfusion in this fragment, and you never observe this variable, you only estimate it through other markers. So let's have a look at that variable. So hypoperfusion is the rectangle and the variable with rectangle shape here, and I'll just use the menu on the left side. Okay, so when I use my browser to get more information about that variable, I get a brief description of what this variable means. It says hypoperfusion is the degree of inadequate oxygen delivery to tissues. Then I have something about excluded BN elements here. Okay. Well, here it says there is evidence that there were other markers of hypoperfusion which we did not include in our model. So it says, for example, respiratory rate and Glasgow Coma score are also markers of hypoperfusion, but we choose to not include them in our model because we thought they were weak markers compared to the markers we have in our model. And we made that model assumption explicit here by like acknowledging it here. And we also put references about respiratory rate and Glasgow Coma scores as being markers if anybody wants to get more information about that. Okay, it redirects to those publications we want. Then the next bit is relations here. The next bit is relations. It shows the parents and child variables of this variable. And if I click to any of those, it will show the evidence, the knowledge behind modeling that arc from hypoperfusion to SPP, for example. And then I have the states of nodes here below that. And then I have the probability distribution, which is a link. I would like to proceed with the probability distribution. So if I click that, the evidence browser will show me the numbers in the hypoperfusion variable. So it shows all the probabilities. This is a discrete node with 3 states, so I can see all the probabilities here. But it also shows where do these numbers come from, and it also shows the rationale for choosing those 3 states. So here it says like these parameters have been learned from the database of Royal London Hospital, and I can like follow the references there and get more information about that database. And it also shows that we chose those 3 states because it was supported by Williams et al. And the method for classifying these states is described by Yet et al. And we can again follow those references and see what the model builders did to get those numbers. Okay, finally, there is also the evidence about relations. So if I have an arc from hypoperfusion to heart rate, it must mean something. And we can also browse that. For example, this part describes why that arc exists in our model. For example, it says when you're in shock, your heart rate increases to sustain the oxygen delivery to blood. And we use that as a mechanism for a marker. But here, it also shows a conflicting evidence. It says, like, in these papers, they said that heart rate is not a good marker of hypoperfusion. So we acknowledge again that knowledge, but we choose to include heart rate as a marker of hypoperfusion. But we still show that, like, a conflicting ideas exist for this problem. So all the references I showed was papers, but like in this model, many of the arcs were related by expert knowledge as well. And in those cases, we just show the credentials of the expert and what expert meant by drawing that arc. Okay, so that was the second bit, the browser bit generated from the evidence structure. And apart from these two things, we can also make completeness queries by using our framework. For example, we can check which variables have evidence or which variables do not have evidence, or which variables have supporting knowledge or assumptions behind them and which do not. And we can use the same old technology to do these kind of queries. Well, thanks for listening. I mean, this work has been published in that paper, and if you want to play with this evidence prober, it's available in GitHub and this link.
Are there any studies of the actual use of this tool? Because my hunch is that doctors would not make use of 99% of the options in your mechanism, in your model.
Okay, thank you for that question. First of all, the doctor doesn't see anything about the technical bit I showed initially. They just see that website. And we made a preliminary study, like we gathered a group of trauma surgeons who were the potential users of this framework and the model. And we presented them the website, and we let them play with the website a little bit. Then we made a preliminary question about their reaction. I mean, would they be more likely to use it, and would they be more likely to use a model supported by this framework? So the initial results were positive, I mean, in that preliminary evaluation, but of course it's not conclusive, and the interface is not perfect now. I mean, we could spend more time and think to make the browsing more user-friendly than it currently is.
Yeah, I like very much what you're doing. One of the questions I have is, so what do you do if there's conflicting evidence about, well, for example, you say, well, there's a kind of dependency here, but the literature, the medical literature, or the kind of other, is unclear about whether there's really a dependency or not, and how do you present that? I mean, because then I assume you would only say, well, based on these papers, we say that there's a dependency, because that's how we modeled it, right?
Yeah, so if there is conflicting evidence, I mean, our aim is to acknowledge it. I mean, these models are, after all, a representation of somebody's worldview, and we stick with one of them, I mean, when we build these models, but we also show that conflicting evidence so that, I mean, if that evidence gets stronger later on, or if it gets completely discredited, I mean, we have a sort of evidence base to show knowledge related to this model. And we don't do anything quantitatively, but we try to show and acknowledge everything. Either it is...
I mean, in theory, you could have kind of two Bayesian networks, right? I mean, if the kind of the jury's out on whether there's a dependency, for example, you could say, well, there's this network and this network, and if you trust more these papers and that kind of stuff, use this network, or if you see what I mean? I mean the choice for which evidence to take into account lies with, well, basically with the one who makes the Bayesian network, which isn't the clinical expert, because they need this to understand it. So that if they would understand it, they would just build it themselves. Right? See what I mean? It's not something I expect you to do in this paper or in this presentation, but it's just something I was thinking about.
Yeah. I think a useful next step would be to have a feedback mechanism from this browser. So when they see the current evidence and they also see some of the conflicting evidence, and they say, well, the conflicting evidence is stronger, maybe you should model it the other way around. Then, of course, the next step would be a Bayesian network expert, I mean the knowledge engineers tasked to modify the model consistent with that input. But I think a useful next step would be to get that input as well after it's like an expert or somebody reads this information. Yeah.
I've actually got a related question to that question. I just quickly, as soon as you asked it, is there a way of weighting somehow the kind of the goodness of evidence, well, the balance of evidence for the different links, and somehow doing, I mean, maybe not in this system, but just in general, I've often wondered about how when you have competing ideas about a link, how you can incorporate that in the same framework, and maybe.
You mean like in the calculations?
You have evidence for the link, rather than just so in the Bayes net or framework, you've got evidence for the link rather than evidence for one of the variables. So the evidence for the link.
Yeah.
Can that? I mean, I don't know. Can that be done in a Bayes net?
Well, actually, in this framework, most of the evidence are about links, because the clinical evidence says that, well, that relation exists or that do not exist. But it doesn't, I mean, maybe a scoring system could somehow be developed to show the ranking of those evidences, relative ranking. But I don't think there is anything to consider like alternative evidence on the arcs with different weights, and then
for example, if I need to decide whether or not to take statins, and there's some people say there is the link, there's disagreements about the different graphs you presented. Can we somehow put that evidence so I can make an overall decision based on the quality of evidence for the different models? All the different.
Yeah, I mean, with this framework you cannot. This framework will show, well, the model follows this school of thought, and if there is also the other one, well, there is a lot of evidence about the other one as well. But if you use this model, you must be aware that we are following that road.
Because it feels like I have to make a decision, which makes a trade-off between the evidence for the different models, and I have to then make a decision. Maybe we could somehow represent that decision problem for me, so I'm in a better position to make the trade-off.
Yeah, I think it will be very useful
it's more a theoretical question.
Yeah.
I think one way to solve your thing would be just to change your probability tables, make them more weak, because if the probability table is a dependence from one node to another, but you say, well, given that proposition, I don't follow that too much, so you can weight that inside a probability table, basically.
But I'd quite like it to be explicit, so that then you can have the evidence explicitly represented for the link, so then you can then overall make a final decision when you're trying to decide. Otherwise, you have to do some kind of, you have to do some of your own kind of way. Sorry.
But in clinical domain, they have this ranking for strength of evidence. They say if it's a trial, it's the strongest, and if it's expert knowledge, if it's the weakest. So We could, for example, put that in there, but I don't think, I mean, for the clinical domain, it would be very useful to use the same scheme. But maybe we need a different scheme to rank the evidence somehow.
Let's see. You have publications giving evidence for supporting the existence of a link.
Yeah, exactly. Yeah.
But then the conditional probability tables, you calculated the probabilities. You, the builders of this system.
Yeah, and we also
give any justification for the values.
Yeah. So when we, okay, let me show that. Sorry. So, I mean, these are the numbers in that table, and here we said like these numbers for this table comes from this data set using this algorithm. Okay, for another table, it could be that okay, these numbers comes from discussions with David Lagnado and Norman Fenton. We just state that. Sorry, yeah, so we just make that clear.
All right.
I was just wondering about the state nodes. So the state's definition. So you define everything, you can click on everything, but I would say that the definition of the different states, it may also be something.
Yeah.
What
So
exactly is meant
for now, we chose to have it here. So this bit here defines we chose compensated and uncompensated due to this paper. But we could have another window for that showing like but I mean right now the definition exists, or at least the rationale for choosing those states exists, but it's inside this same window with the numbers.
I'm going back to my previous point. So I understand that if we're going to make a 24 hours operation, we should study all the evidence. But you're talking about trauma. I wouldn't. If I'm a patient in the trauma room, I wouldn't like the physicians to start browsing your.
So no, in the trauma, the patient will never use the model. It will be the doctors or.
I wouldn't like the doctor to do it.
Yeah, of course. And in that case, I mean, you wouldn't like.
But by the time he finishes, you won't be there anymore.
But sorry, if you are in trauma, I mean, believe me, you would like doctors to do it because you won't have enough conscience to make your own decisions. I mean, that's what happens
I
more
would probably be happier if there would be an experienced doctor working on his heuristics, on his expertise.
But these models are developed for experienced doctors as decision support systems. These are not expert systems acting alone, okay? These are not like robots making decisions for us. It's just like making predictions based on the extensive literature and knowledge for the doctor, and it's the doctor's decision to how to use that output. He may choose to use it, he may choose to refuse it, he may choose to, I mean, if it fits with his heuristics, I mean, that may make his argument stronger, but it's not in, I mean, any place doing something on its own.
As I understand it, it's the way it can be used. If there's somebody in trauma, you just click a few observations, right? And so that's what the doctor needs to do with the patient. And whether he trusts the model, well, he can do that in the evening at home. And
Yeah, he's not browsing this real time, yeah. I think,
Reading papers.
yeah.
Hold on, I'm halfway through this paper.
The patient bleeding.
I think it can, I mean, for this case, it can even be an institutional decision. So, like, as the trauma department, all of them review it, discuss it, and then after all, they decide to, like, have this in the emergency department or not.
William?
Can I just add a remark into this? I mean, if we're able to make these models refutable, then of course medical knowledge advances. And so one of the aims would be to detect when the model is no longer consistent with the latest medical knowledge. when it needs to be updated in the light of new knowledge. And we might even bring more automation on that. We've now got a set of papers that support the evidence, and of course we could automate when further publications are produced that reference these papers, for example.
Thank you very much. No more questions? Thank you very much.
Thank you.